Yes.
Okay. Now what we used to work with, just rectangular beam. We did for the cracked section, we did a T section, and then we did the rectangular section. When we have the reinforcing, trying to find out the capacity of the beam, we did only rectangular section, but we didn't do the T section yet. So in this slide set here, we're going to start to learn about T beams. When you have a case of a T or an L shape, we still call it T beam in the code. And when it says here doubly reinforced, it does mean that you have a couple of rebars next to each other, but it means that you have reinforcement in the tension side and compression side. So let's say tension side, usually when we have passive moment, tension is going to be at the bottom, compression at the top. It means here that you're going to have tension reinforcing and compression reinforcing in the same beam. And then we need to learn here how to handle both of them. Just explain the meaning here of a T-beam. Almost all beam that you are going to be working with is going to be a T-beam. Look at this one here. Here's a beam. It has a slab connected to it. Now, depth of the beam is going to be the distance from the bottom of the beam to the top of the concrete slab. Someone may think and say, is it from here, we're going to put here a line, to here? You say no. Depth of the beam is going to be from here all the way to this point, to the top of the beam. It's going to be the beam depth, right? This distance from this red line to this red line. It's going to be the beam depth. How about the beam width? Beam width, I'm going to say, is going to be from here, from this face, all the way to this face. That's what you call here rectangular section. Now, because the slab is attached to the beam, it's going to be poured in the same time with it. And this is what you call here monolithic construction. And because also usually compression is going to be in the top flange, I'm going to say we have here a certain piece of the concrete slab. Let's say from here all the way to here. It's going to be acting as part of the beam. So now the beam becomes a T section instead of having it a rectangular section. It is very common in engineers, between engineers, that if you'd like to start here a design, you just consider the beam to be a rectangular section. And in the final design stage, you consider it to be a T section. Now, which one do you guys think is going to have a better performance and higher capacity? Is it going to be the T section or rectangular section? I'd like to hear from you.
Better performance in compression, you mean?
What I'm saying is, if you compare here between this rectangular section and between exactly same section with the same reinforcing, but the other case here is going to have this concrete flange, which one do you think is going to be stronger, the T or the rectangular section?
I think the T is going to be stronger because it moves the neutral axis a little bit above from the rectangular. Then there's going to be actually that the C is going to be smaller, then it's going to be as greater resistance.
You mean C lowercase neutral axis depth, right?
Yes.
All right. This is a very good answer. Also, I'd like to simplify it if you don't mind. I'm going to say here that here T section is going to be stronger. Why? Because you have taken this rectangular section and then you came at the area of compression, you start to add here more material. So the compression is going to be stronger in compression, which means most likely the beam is going to be stronger. Does this make sense to everyone?
Can you repeat that, Professor?
Yeah. Difference between the two sections. Going to be taking you here. Here's the beam that you're talking about, right? It's going to be the beam. In reality, this beam, it has a slab connected to it. So someone's going to come and say, this is going to be my beam. Ignore the flange. Another person, so I'm going to say, okay, here's one option. Another person is going to come here and say, no, my beam is going to be like this. Let me just put it in one line. You say, my beam is going to be like this. Just fix it to align it with this. Now, which beam do you think is going to be stronger here in this case? Now, reinforcing, I'm not going to change the reinforcing. It's going to be the same. All tension rebars is going to be the same. Now, which one, in your opinion, is going to be stronger? Is it going to be the rectangular assumption or the T assumption? Oscar?
The T section.
T section. And the reason is because if you like to compare this to this, if you like to make this, let's say, in blue, you're going to come here and say, this beam here is just larger, the red one. It's all the same size when it comes to the depth, same width for the web, but for the flange it's going to be stronger. So I would say definitely the red beam, which is the T beam, is going to be stronger. So when an engineer is starting his design at the early stage, he's going to consider the beam to be a rectangular section. Reasons because it's just simple when it comes to analysis. It's going to be very simple, like the way we have done it. You can just do it maybe in 2-3 minutes, maybe 5 minutes max. He's going to be done with the design of the section. In the final design stage, to determine the actual strength of the beam, you're going to do it like this T section. So you're going to have a little bit of more work, detailed analysis, but you know what? Now you know the depth, you know the width, and approximately the reinforcement is kind of set. Now we understand why we can ignore the fact that all beams are T beams and just consider to be rectangular section, just for simplicity at the beginning of the design. Any questions? We're good? Okay. Here's the plan view. We call this grid lines like 1, 2, and 3, and the spacing is given A, B, and C. And then we have columns. This light blue is going to be the column location. Looking from the top, this like plan view, we have concrete slab, and the concrete slab is going to be spanning in this direction, which means the load is going to be coming here. If you put a point load right here at this location, it's going to be going right and left. It's going to be so tough for it to go this way and that way. So we call this one-way slab. We talked briefly about this before, but we're going to be also going through more details about it. This is now is going to be a slab panel. This is going to be another panel next to it. And then a third panel, fourth panel, so forth. Look for each one of these panels. I'm going to be taking this out. Find out the aspect ratio. Aspect ratio means length to width ratio. So what is the length of this one? You can say roughly 32 feet. How about the width? You can say roughly maybe 15 feet, provided I'm going to be taking it to the center of the beam if you want to. So I'm close to be 15, close to be for the width, and this is going to be about 32. If the aspect ratio is equal to 2 or more, I'm going to be calling it one-way slab. So I'm going to put it right here. F L divided by B is more than or equal to, I'm going to call it one-way slab. Make sense? If this length here is 2 or more, this length or this width, I'm going to call it here a TB. Meaning, if I have a concrete slab like this, like aspect ratio 1 to 1, I'm going to put it right here, right? I'm expecting that the load is going to be moving this way. Part of it is going to be coming this way. Some load is going to be coming this way, and some load is going to be coming this way. And all the loads are going to be equal. Why? Because the aspect ratio is equal to 1. The length by width ratio is equal to 1. In this concrete slab, when it is one way, 1/2 the load is going to be coming this way, and 1/2 the load is going to be coming this way. Almost nothing is going to be going in that way, because the load here is looking for the shortest distance to get transferred. As long as the aspect ratio is going to be equal to 2 or more, you're going to have one-way slab and you're not gonna have this two-way slab action. So now I understand that I'm gonna have here one-way slab in all of these cases, right? And usually you're gonna have here the load is gonna be going from the slab to this beam, to each one of these beams. Now the beam is gonna be taking the load and move it to, let's say here's this beam that we're talking about. Load is gonna be going that way through the beam, and also through the beam, one point reaction is gonna be coming that way. How about this beam here? You're gonna say in this beam, the load is gonna be going directly to the column in this side and directly to the column in this side. How about this point load at this point load? You're gonna say this point load here goes to this girder. So here's the difference between a beam and a girder. A beam usually supports the slab directly. The girder usually supports the beam. So I'm gonna call this a girder, I'm gonna call this a beam. And here's the name. You see this girder, and this gonna be the beam, and this gonna be the column. Now in the girder, load eventually is gonna be going to the column this way, and also going to the column in that way. Same thing for this guy here. Gonna be exactly the same distribution. Which means one half of the load is gonna be coming this way, and the other half is gonna be coming this way. Okay. Now let's cut this section here, AA. When you cut the section AA, what do you see? You say, look at this. You're going to see all of these beams to be a T-beam. It's going to be a T-beam, a T-beam, a T-beam. But when you cut the section here, you're going to see an L section. It's going to look like an L shape. And this is exactly what you look here at. This beam here is going to be like an L-shaped beam. When it comes to analysis, we're going to analyze it exactly the same way that we do in the T-beam. And the code would just call it a T-beam in this case. So we understand the difference between the rectangular section and a T section. Rectangular section is going to have the entire depth, entire width, web. In the T section, you're going to have a concrete flange that sticks right and left, or just on one side if you have an L beam or an L shape. And the question is, how much of the slab would you consider to have this effective flange width? Like from here, how did you come up with this width for the slab? Let's say if I have a situation like this section here, the first thing I'm going to be thinking about, I'm going to say, let me take it here half the way from this beam to that beam. I'm going to say, now this piece here belongs to this beam, and same thing from this side. I'm going to say, this piece here belongs to this beam, and this piece here belongs to that beam. So my section now is going to be this way. I'm going to say, now let me take this out. Let me take this out. Here's my rectangular section. Just gonna extend it here all the way to, if I can. So here's my beam. Let's give it from half the way. Like half the way, roughly. This gives my T-beam. So the first thing about here, the width of the flange, I'm going to be taking it half the way from one beam to one beam. Now, how about here? Now, where is going to be the flange width? Flange width here is going to be almost equal to 15 feet. Why? Because I'm going to be taking it from this line. I can do it here, all the way to this line. It's going to be the flange width throughout here. So I'm going to say, okay. How about in this case here? For this beam, where is the slab width? You say slab width here is going to be equal to 10 feet. From here to here. And the distance is going to be 10 feet and 10 feet, so that from here to here is going to be 10 feet. So I'm going to call this maybe the boundaries between beams, tributary width between a beam and the other, right? But this is not it. The slab thickness also is going to be a factor. And in the code, it says that you need to take certain width based on the slab thickness, the tributary width, and a fraction of the span. We're going to be going through this later on But for now, I'd like to confirm here that the maximum flange width is going to be equal to the natural boundaries, which means the spacing from another beam to another beam. We call this tributary width, if you like. Now, here's what we have now. If you have a T section, you're going to have the flange thickness, right, which is HF for the flange. Sometimes you hear it as TS. What is TS coming from? T sub S. T is going to be for the thickness, and S is going to be for the slab. T sub S is going to be the slab thickness. The depth to the tension rebars is going to be the same. It's going to be this D, the one that we used to use. AS is going to be the tension reinforcing, total cross-sectional area of the tensor reinforcing. BW, and instead of B in the rectangular section, now we're going to call it BW, which is the width of the web. To be sure that we differentiate between BW and B. So if you have a rectangular section, you can call this width here to be BW or B. But if you have a T section, this symbol B sub W is going to be reserved for the web width, and just B is going to be reserved for the flange width. Any questions? You're good? Amin? You have a question, Amin?
Professor, so if you go back one slide, the effective flange width B. So in that, yeah, in where your cursor is, will the width there be 10?
Yes. It's going to be one of the limits. There are other limits. It also depends on the slab thickness that we don't have it, and also depends on the beam span. So we're going to have some other factors, and then we're going to take it to be the smallest of the following. But this is going to be one of the limits, which means from a beam to a beam, or tributary width to a tributary width. Good question. Thank you. Yes, Amin, you have a question, Amin?
No.
Okay. All right. You're with us. Okay. All right. So in this section here that you're looking at, it is a T section, but there is no compression reinforcement, which means in reality, I'm going to see a T section with also compression reinforcement. I'm going to have here doubly reinforced section, and also a T section. This is going to be the reality. You can simplify it by assuming that this is only a rectangular section with some tension reinforcing, which means that you can ignore the compression reinforcing if you want to, and also you can ignore the fact that this is a T and just treat it as a rectangular section. Usually this simplification is made at the initial stage of the design. But once you know the width and the depth, most likely you're going to have a software or maybe a spreadsheet that you can do all of this analysis for you. So it is not going to be that complicated when it comes to actual practice. But in this case here, and for our level, we need to know how to do everything here by hand. All right, section analysis. I guess you guys have seen this slide before. There's nothing here new. In the section analysis, we're going to have the maximum compression strain in the concrete is going to be 0.03. This is where the section failed. So this is going to be like the capacity point. Neutral axis depth is going to be equal to C, lowercase. Usually we assume that the strain in the steel is going to be larger than the yield strain. And therefore, the tension in the steel is going to be equal to the cross-section area of all the rebars multiplied by the yield strength of the steel, which is usually 60 kSi. Compression now, block depth is going to be equal to A lowercase, which is equal to beta 1, a factor which is based on concrete strength, times C. And total compression force is going to be 0.85 F prime C B times A, nothing new here. Location of this compression force is going to be right in the middle of the compression block. And C is going to be equal to T, nothing new. This is exactly what we have done before in our rectangular section analysis. And then your moment M sub n is going to be either equal to T or C times the distance from the C to T, which is equal to what? It's going to be D minus A over 2. Once you find M sub n, you find C, you can divide by D, and then you can find out the phi factor value. Or you can find out the strain in the steel. And then again, you find out the phi factor. This is exactly what we have done in rectangular section. And we're going to be repeating it for the T section. But it's going to be some tricks in there. Same equations, nothing here is new. Here's the tension force, compression force, set them equal to each other. You have the reinforcing, you have F sub Y, you have B, you have the concrete strength, you find out A. Once you find out A and then you do the phi factor, you can do Mn and then you do phi Mn. So nothing here is new. Now let's see how this is going to get done when you have a concrete section like this, a T section exposed to some flexure. Now our goal here is to find out phi Mn. In this section here, depth is given. It says it's going to be 12 inches, not the total depth. It's going to be depth to the tension rebars. And they say that we have here 3 number 9 rebars. Total cross-section area is going to be 3 square inches. We know that number 9, it has a cross-section area of 1 square inch. We know this from the steel table, the rebar table. You guys recall the rebar table?
Yeah.
It's right here. In the first slide set, slide number 24. Number 9, it has cross-section area of 1. I'm not going to be using this. This is the diameter. I'm going to be using this 1 square inch. The width is going to be 10 inches, given. All of this information is given to you. Flange width, 32 inches. It's given. So I'm not going to be asking about tributary width or the beam spacing. I'm not going to be asking about this. It was just given to me. Slab thickness is very small. As it says here, 2 inch thick. Very small slab. So right now, what I need to do is to find out the A, which is a compression block depth. I have 2 options when I calculate A lowercase. One option, that A is going to be right here, like the location shown there. And in this case, I'm going to be looking here at this hatchet section. It looks like a T section. I'm going to call it, in this case, this is a T section for the analysis purpose. I may run the analysis in a different beam or very similar beam, and I can maybe find out that the neutral axis depth is going to be right here, which means A is going to be here. It's going to be smaller than the slab thickness. So let's assume for a second here that I did my analysis and A was equal to 1.5 inch, less than 2 inches. In this case, I'm going to be looking here at the section exposed to compression. It's going to be this rectangular section. In this case, I'm going to be calling this section. We'll come to the analysis. I'm going to be calling it rectangular section, not a T section. Not very clear. I understand. But we're going to get to that. I'm going to say here, let me do the analysis. Forget about this location, forget about this section. Strength of the concrete 3000, F sub Y is 60. Let me find out A, the concrete block depth. How can I find this? I'm going to set compression is going to be equal to tension. Therefore, A equals to AS Fy. AS is going to be the 3. And Fy is going to be equal to 60 KSI divided by 0.85 times 3 KSI for the strength of the concrete, divided by B, which is the flange thickness in this case. This is going to be the width exposed to compression. So I'm going to say this is going to be the width B, 32 inch. Now depth here of the compression block is equal to 2.2. Slab thickness is 2 inches. Then this picture here makes sense. A is going to be slightly deeper than HF, the 2 inches. So this little distance from here to there is going to be equal to 0.2 inches from here to there. So I really have a T section. Now, can someone help me here quick and tell me how much is this area of the concrete? Can someone help me quick for this? Yes?
Is it 66?
66. How did you do it?
The area of the upper area, 32 by
Yes.
2.
Yes.
And then I added the 10 times 0.2.
Very good. 66 square inches. How much was the tension in the steel originally when I did this analysis? Can you help me with this? AS is equal to 3 and F sub y equals 60. 180 kips. When I say T is equal to C, I find out that A is equal to 2.2. And the cross-section area here exposed to compression is going to be 66 square inches. And my understanding that it has uniform compression stress of 0.85 F prime C. Now it means if you're going to be taking here this 0.85 F prime C times 3 times this 66, I should end up with 180 kips. Don't you guys agree? Yes or no? I'd like to hear more than one person. Would I end up with 180 kips?
No.
Why not?
I got 168.3.
What is happening? What's wrong? Why it is lower? I thought that we were going to set compression equals to tension. This is exactly what I've done. I put here the compression is going to be 0.85 times AS times F sub y. I want to hear from you guys. What's going on? What's wrong? I'm going to put this old slide set.
I'm sorry, Professor. You said that the area for the concrete is 66. Is that the shaded portion?
Yeah.
So
Okay. Here's the equation. Do you see the equation? Anything wrong with this equation?
I'm just backtracking.
Yes. Yeah. But anything is wrong with this equation. I want you to double check it with me. I may do a mistake. You know.
So we did 32 times the 2, and as well as the other area with A1 times the base, right? And
Yeah.
yeah. That's the total area.
So this is going to be 168. This is going to be for the compression, right? Kips. They are not equal to each other. I thought that this number, right, is going to be the same as this number here, correct? But they are not. Let me try this previous example that we have solved in slide set number 3. All right? Let's do the same thing. I'm going to say here, AS times FY. I need your help with me. AS times FY. How much is this in this example? Who can help with this? RJ, can you help me?
It's 180.
It's going to be how much, RJ? He's not there? Okay.
It's 180.
RJ, I heard you. Thank you, Hudiva.
Oh, I'm sorry.
RJ, are you there? Okay, RJ. Hey, Alan Bond, I need your help here to find out the tension in the steel in this example. Alan Bond?
Yes, Professor.
Yes, I need your help to find out the tension here. How much is the tension? in this example, which is right in front of you, this one. Can you help me with this?
Sorry, Professor, but I'm still a little confused. I'm not 100% sure how to do it.
Okay. Okay. How do you find out the tension in the steel? Do you know in general terms how it works?
Excuse me, is there anything with the T section that added to that, because the difference is because of that?
Okay, I'm working now on this example. I appreciate your input here about the previous example, but now I'm working on this. I wanted to do the tension compression on this example, previous example, in slide set number 3. This is the one that we have done already. So I'd like to hear from Alan Bond, how the tension in this reinforcing is calculated. You can say pass. If you don't know, no sweat, just say pass. I don't know how to do it.
Sorry, I don't know how to do it.
All right, Alan. Alexis, can you help me with this?
Sure, I'll give it my best
Right.
shot.
So how do you find out the tension in this, in the reinforcing bars on the bottom?
So kind of knowing that due to the compressive force of the top, the steel is going to bend up. So I'm guessing the tension is just going to be AS times FY,
Okay. Which is AS?
which is the 142.2 kips.
Oh, this is going to be the tension. All right. So you give me here the tension right away. You just read it from here, which is good. At least you're looking here and you're reading what you are working on. 142.2 kips. How much is the A value that we ended up with? A value in this example, can you see it? You see the number here? Okay. So I'm going to say, how much is the area of the concrete?
10 by 16, so
10 by area of the concrete exposed to compression, 10 times 4.18. Do you guys know where I get this number from?
from A.
This could be the 4.18 times the width. All right? How about the compression force? Adolfo, can you help me with the compression force? Thank you, Alexis. Thank you. Adolfo.
Yeah.
Can you help me with the compression force? If you know the area exposed to compression, how do you find out the compression force?
0.85, the cracking force.
How much is the concrete strength? Can you see it here, somewhere here? Can you see it here?
Is it 4 or KSI?
Yeah, 4 times what? How much is the area of the concrete that's exposed to this compression?
It's your A value, so it's 4.18 times the width.
10. Excellent. Thank you. So look at this. Look at this value here. The tension force is 142.2. Compression force 142.12. Very close. We have just some approximation here in the compression block depth. And this makes sense. They are equal to each other. All right? Now we understand what I'm doing, I guess. Let's go here to our example, the T section. I'm gonna redo this again. I'm gonna say, okay, AS times FY is equal to what? Look at this number here. 3 number 9, which means 3 square inches times 60, F sub Y is gonna be 60 times 3, 180 kips. With that, I was able to find out the compression block depth, which is 2.2, slightly deeper than this section, which means the flange thickness. I'm gonna find here this shaded area or hatched area. I'm gonna say it's gonna be 32 times 2 inch plus 0.2, which is this little drop You see this little drop times the width, 10 inches. It's going to be 66 square inches. You see this equation? It's going to be right there. Now compression force is going to be equal to this area of the flange or area of compression multiplied by 0.85 times 3, which is 3 KSI. I'm ending up with 168. You are talking here about almost 11.7, like 12 kips difference. What happened? What is wrong with my equation? Now I need your help. Can someone help me with this? Yes?
I think that the T section that add to this system actually decrease the compression force and yeah, I think that's going to be because of that T section.
Let me tell you what happened. What happened in finding the compression block depth A, I divide by the width B, and B, the one I used in my equation, is equal to 32 inches, which means I assumed that this is going to be my section exposed to compression, the whole thing. You guys agree or no? Not really.
Sorry, so you said that the area that is hatched, that one is subject to a compressive force?
Yeah, this is what we have. This hatched area is the actual area exposed to compression force. But in my analysis here, if you use 32 inch for the width, it means that the green shaded area is going to be exposed to compression. Why? Because I simply said, according to this equation, if you want to find out the compression force, right? Compression force actually equal to 32 times 3 times 0.85 times 2.2. This is what I'm saying. So let me show you here the artificial C that's not really correct. Here's the C, if you like to use my equation. It's going to be 32 times 3 times 0.85 times 2.2. Look at this. 179.5, almost equals to 180 with the rounding up for the numbers, right? So if I use this equation here, it makes sense. But if I'd like to find out the actual area exposed to compression, right, is going to be equal to 66 square inches. But the area that I assumed is going to be exposed to compression, but this doesn't happen to be correct, is going to be equal to 2.2 times 32 inch. It's going to be 70. So in my analysis here, I assume that the area exposed to compression is going to be 2.2 times 32 inches, 70.4. Reality that I have a T section and the compression block depth is going to be deeper than the slab thickness, and the actual area exposed to compression is going to be equal to 66 square inches. Now, where is this coming from? It is coming from this hatched area. So the difference in the problem that I have in my assumption, I assumed that all of this green shaded area is going to be exposed to compression. Reality, I don't have this piece here. Look at the difference between the hatching and the shading. It's going to be this little bit of an area here, right? This here causes the discrepancy in my analysis. This is why in the tension I'm receiving here 168, because I took this out. I took this little area, the difference between the shading and the hatching, I just ignored it. I just took it out. This is the reason that my analysis here is incorrect.
We also consider that those two areas.
These two little areas
Yeah.
are assumed to be in compression if you look at this equation, correct?
Okay.
When you look at this equation here, it says compression area equals 32 times 2.2, which means the whole green shaded area. But when I went back and I wanted to calculate out the area exposed to compression, I just used this area here, the hatched area, correct? In the given example. And this created here the discrepancy in my analysis. Which means my analysis here for the 2.2 is incorrect. And this section, or A, is going to be deeper than 2.2 because I need to set at the end tension is going to be equal to compression. So, okay. Let me move forward and see what's going to happen. And now, how can I do it in the correct way? I'm going to say, you know what? This area here, I know that neutral axis depth, or the A compression block depth, is more than 2 inches. And I think it's going to be 2.2. But this is incorrect because now tension is not equal to compression. This tension force, as calculated out, like what you see here in the spreadsheet, I calculated it out to be 180. When I did the hatchet area, it turned to be 168. They are not equal to each other. So I need to have more compression. The only way to gain more compression, if you move this A down a little bit, so you gain more area exposed to compression. How this is going to get done? Just look here at this diagram. And instead of having one compression force, I'm going to have 2 compression forces. One of them is going to be going to A sub 1, which means a flange only. And how much is the area of the flange? You say 2 times 32. It's going to be 64 square inches. How about A sub 2? You can say, okay, A sub 2. How can I do this A sub 2? I don't know the depth yet. This total depth is wrong. The 2.2 is wrong. The 2.2 that you are looking here at is incorrect. It's not exact. And it causes discrepancy in the tension compression force. So I'm going to say, now I have this unknown, which is called A sub 2. What is A sub 2? A sub 2 is going to be equal to A subtracting 2 inches. And this A sub 2 is going to be equal to 10 times A sub 2. This is going to be A2. So this A2 uppercase, this area of the subsection 2, this area of the web exposed to compression is going to be equal to A lowercase sub 2 multiplied by 10 inches. As you see here, A2 is going to be equal to 10 times A sub 2. All of these 2 areas, both of them exposed to 0.85 A prime C. And with that, I can have here 2 compression forces. The first one, I'm going to call it N, like normal force. C, compression in the flange. And this one here is going to be N, which means normal force, compression in the web. So this here force is going to be right in the middle of this section. It's going to be like this. And this force here is going to be right in the middle, right here. So I'm going to end up with 2 forces.
Professor, would you mind
Yes.
explaining a little bit more what you mean by A2 is equal to 10 times A2? So I understand that the 10 is the width times A2, and I'm confused with why the 2 inches, the reference axis, why when we subtract them, we don't know the value.
Okay, coming to you on this.
Okay, thanks.
No problem. Good question. Thank you. All right. Now I know neutral axis is going to be right here, somewhere here, right?
Mm-hmm.
And I know that the compression block depth A is going to be here. But I don't know this value 2.66 yet.
Oh, okay.
All right. So I don't know this A. So I'm going to say, you know what? This is going to be what? Let me put it here. I'm going to call this A lowercase. This A is greater than 2 inches. So I can put here an equation. I'm going to say A equals 2 inch plus A sub 2. A sub 2, which is this one here. I just give it a symbol. I call this A sub 2, right? I can pick the symbol I want to. You can call it Y, you can call it K, you can pick any symbol for it.
Mm-hmm.
But I decide to put it as A sub 2. Now, how much is A1, A, which is the cross-section area, A sub 1, A uppercase? You see this equal to 32 times 2 inch, correct? Not going to change. How about this A2 for the yellow area is equal to what? Is equal to 10 inch multiplied by A lowercase 2, correct? It's going to be equal to this yellow shaded area, right? How much is this? The yellow shaded area is what? Is equal to this width multiplied by this depth. And this depth is equal to, is a symbol that I picked here in my analysis. I called it A sub 2.
Right,
Therefore,
okay.
A2, which is a cross-section area number 2, is equal to 10 times A sub 2. You're good?
Yep. Thank you so much.
Great. Thank you for the question. Very good question. Now, the tension force is going to be a constant in my analysis. Let me put it back. Tension force here is equal to 180, correct? How about the compression force? I'm going to say compression force now is going to be composed of two compression forces. This plus this. So I'm going to say this tension force, 180 kips, equals NCF plus NCW. This guy here is going to be equal to this too. NCF is simple. I'm going to say NCF is equal to A1, the 64, times 0.85 A prime C. So I have this value. I have numerical value for this. NCW equals to what? 10 times A2 times 0.85 times A prime C. When you set here tension is going to be equal to compression, you're going to have only one unknown, which is this A sub 2. Let's see the equation. Here's NCF, or you may call it CF, like compression the flange. You know, usually, I'm going to just take you back here quick. In the past, we used to call this just C. When you open the book, the reference book, they called N sub C. This is the same thing. So C or T or N sub C, N sub T is the same thing. So I'm going to say here, C sub F, the compression the flange, is going to be equal to 0.85 F prime C times the cross-section area of this flange. Cross-section area of the flange, as we agree, is going to be equal to 64. I'm going to take you back here one slide. Here it is, 64 square inches. Times 3, the F prime C, times 0.85. So I know that this is going to be 163.2 kips, right? This is going to be compression the flange. Compression now in the web is going to be equal to 0.85 F prime C times A sub 2. I'm going to take you here back one slide again. Yeah, compression here, NCW or C sub W is going to be equal to A sub 2 times 0.85 F prime C. So, okay, here's the equation. 0.85 F prime C times A2, which is the same as equal to the tension minus the compression on the top. Why? Because I simply can say here, let me type it here. I'm going to say, I understand that T equals to NCF plus NCW. This makes sense? Yes? No?
Can you make that a little bigger?
Yeah. How about that? For some reason, font is, I don't know what's wrong with the font. It doesn't give me a chance to change it here for some reason. So I'm just going to keep it this way. So is this equation correct? I'd like to confirm this. So I'm going to go back here to my slide. Here's the equation. It says the tension force is going to be equal to NCF plus NCW. This makes sense because total tension is going to be equal to total compression. Tension is going to be just one force. If you like, you can call it N sub T, if you like, just to be uniform with this, consistent with the symbols. So I'm going to say N sub T equals NCF plus NCW. So, okay, good. This is going to be my equation that I'd like to use. I'm going to put it here. Do you have NT? Do you have the tension force? I'd like to hear from you guys. Do we have the tension force?
Yes.
It's going to be 180 kips, correct? So I'm going to say, okay, it means that 180 kips equals, this is going to be the tension force. It is equal to The compression force in the flange, do we have it? You can say yes. It's going to be 163.2 plus the compression force in the web. How much is the compression force in the web? You can say it's going to be equal to 0.85 times 3. What's 3? F prime C times A sub 2 times 10. Do you guys agree with this equation or no?
Yes.
Let me put it here. What I'm saying is, the tension force here is 180 kips. The force in the flange is 163.2, calculated right here. The force in the web is going to be 0.85 times F prime C the 3 times A sub 2 times 10 inch, which is A sub 2 lowercase times 10 inch, the width. Okay, I'm going to say, okay, let me go back here and confirm. This tension force, the 180 kips, equals compression force in the flange 163. Oh. Plus the compression force on the web. Compression force on the web is what? 0.85 F prime C times A sub 2 uppercase. What is A sub 2 uppercase? It's going to be equal to 10 multiplied by A sub 2 lowercase. With that, I have this equation here that has only one unknown. So let me move it here aside and say in this equation here, I have only one unknown. What is the unknown in this case? Can someone help me here with this?
A sub 2.
A sub 2. I can solve for it. And here's the analysis. A sub 2 equals to what? 0.66 inch. It is not 0.2. Correct? In the previous analysis, this A sub 2 here is equal to 0.2. Why? Because I said that A is equal to 2.2. Subtract 2 inches, is going to be only 0.2. In the correct analysis, in the exact analysis, turned to be 0.66 inches. Let me go back here to my analysis. If you recall this analysis that I have done, again, just redo it here now for the new case. You can say, you know what? Let me figure this out. Tension is going to be the same, 180 kips. A sub F is not going to be equal to 66. It's going to be equal, look at this. Now this is going to be 0.66, right? Look what happened. This area now, if I use this equation, 32 times 2 for the flange and 0.66 times 10 for the web area, it's going to be a total of 70.6 times 0.85 F prime C. It gives me 180.03, which is exactly this number. Now the tension is equal to compression. Are we good or not really? Anything that I need to repeat?
Very good.
All right, great. How about the phi factor? You can say, well, how much is A? The A lowercase. A lowercase is going to be from here to there, right? And the C, neutral axis depth, which is from this line to the top, is going to be equal to 2.66 divided by 0.85. It's going to be 3.13. How much C over D? As it says here, you divide by 12, it's going to be 0.26. Let me look here. 0.26, here's C over D. Which way are we growing in this number here? This number grows this way, so 0.26 is going to be here, which means strain in the steel is going to be higher than 0.005. So my assumption that the strain in the steel is going to be greater than F sub Y is correct. And also, based on this C over D, I have a phi factor of 0.9. So great. So what to do next? To do next, I need to find out the moment capacity, Mn. Now in this case, take the moment about the tension force. So I'm gonna have here two forces. One of them is gonna be the flange force. I'm gonna need here ZF. Another one, I need ZW. What is ZF? ZF is gonna be the distance Z from the tension all the way to the compression in the flange. This is why they call it ZF. How about ZW? It's gonna be distance from the tension force all the way to the compression and the web. That's why they call it ZW for the web. So fine. How about at the end? How much the moment is going to be equal to? What is the equation for the moment? I'm going to say equation for the moment is going to be similar to that example at which we have used 3 compression forces and 1 tension force. Anyone recall this example? Yes or no?
Yes.
Like in this example. Slide set number 2, slide number 19, and this slide here. You have here Z1, Z2, Z3, and then you say moment is going to be equal to compression times Z, compression times Z, compression, and then you add them all up together. You're going to be doing exactly the same thing here. How about ZF? How do you do ZF? ZF is equal to what? Can someone do the analysis for quick for the ZF? The ZF. How much is that? Distance from, yeah?
12 minus 2 divided by 2.
Yeah, which is how much?
11.
11 inches. Very good. Okay. Here's the distance ZF, 11 inches. Distance ZW is going to be 12, subtracting the 2" for the flange, subtracting A over 2. I'm going to say, what do you mean? I'm going to say distance from here to there is going to be equal to 12 inch minus 2 inches. Distance from here to there is going to be 10 inches. You subtract the 0.66 over 2. That's okay. Here's the distance CW, 967. Now, where is the moment capacity? I'm going to say, okay, it's going to be the phi factor, 0.9. You have compression force times Z plus compression force times its Z, and then you divide this by 12 to put it in kfoot. Here we go. Here's the moment capacity for that section. Any questions? No questions? All right, now let's go here to the homework. This homework, you guys, you have solved this already. And here it says in problem number 1, please give me your attention because this homework you need to redo another problem very similar to it that I posted already. And you guys know when this is gonna be due? This is gonna be homework 3B. Would you please look at this? Now we have discussed it. I showed the date due. It's very clear. It's gonna be this September 17th. What is September 17th?
Thursday.
Thursday. Okay, good. So this is not Sunday. I don't want people to come confused and say, oh, I didn't know it. It was not clear to me. Please be careful about this. Now to review this with you, it says here determine the model rupture, FR. Can someone help me with this? Tell me how do you find this out?
7.5.
Square root of F prime C. Thank you.
That's useful.
How about the section modulus? Do you know how to find it?
Is BH 3/12?
Yeah, very good. How about the cracking moment based on this section modulus and modulus of rupture? What is the equation that you do to find it?
To what? To find what?
To find out the cracking moment.
I use MCR is over S is equal to FCR, and then just manipulate that.
Excellent.
That's actually flexure formula.
The flexure formula, very good. How about this internal forces? I guess based on the stress, you should be able to find out the internal force, correct? And then find out the moment. And this moment needs to be exactly the same as this moment. The two different methods that we have studied, there is no third method that you're not aware of. How about in here? This is now problem number 2, completely different from the requirements that you see here. Now it gives you here this beam, and it says here ignore the self weight of the beam, correct? If you have a case like this and the loads are given, it says here ignore the self weight of the beam, and they determine the maximum moment. Now maximum moment is going to be based on this given beam and loading. It has nothing yet to do with this. So no one's going to be confused between M cracking that you have just calculated out and this moment, maximum moment, based on this structure given to you. So what's next? Check if the beam has cracked. What does it mean by that? It means that you're going to be calculating the cracking moment and the applied moment to the beam. If this applied moment is larger than the cracking moment, it means the beam has cracked. If this applied moment is less than this cracking moment, it means the beam didn't crack yet. Are we good about this?
Mm-hmm.
All right.
Yes.
Let's see what's going to happen in this homework 3B. I guess you know why I called it 3B. Okay. Sound the same. Look at this. Is it the same? Almost, yeah. Everything here is going to be the same, which means if you have done this successfully, or if you tried and you didn't do it successfully, maybe you're going to have a better chance here to enhance your grade for this homework. So here's what happens. Do F sub R. Yeah, I've just done it. I've just done it here. So what is the difference? This is 5,000, this is here 6,000. Correct? Moment of inertia for this section. How about the rebars? Do you need to consider the rebars in your analysis when you have a cracked section?
Yes.
No. When you have uncracked section, you don't consider it. If you have cracked section, you consider it, right?
Mm-hmm.
Now, this is going to be uncracked section. In your analysis, the whole homework here is going to be about uncracked. So this rebar doesn't count. Can you find out the centroid of this section? Yeah.
Mm-hmm.
You guys, you studied this in the statics, mechanics of materials. Do you know how to find out S? How to find the tensile and compressive forces in the concrete, internal? Same thing, exactly. Also here, ignore the self weight of the beam, even if I didn't tell you. Just ignore it, right? Okay. So we're going to find here the cracking moment. It says in this problem here is the loading, P and P. What is the maximum load that this P or this beam can support without cracking or at the cracking limit? How much is the moment here? Can someone give me here the moment? Acting on this beam, what is the maximum moment? M is equal to what?
P times 10.
Thank you, very good. So this can be the maximum moment, right? So what do you need to do to find out this vertical load is going to be causing this beam to crack? You're going to say this moment here, which means 10 times P equals to M cracking. Where'd you get M cracking from? Oh, you get from here. You solve from here, right? Once you solve from here, you set them equal to each other, or in other words, you take this cracking moment, divide this by 10. It's going to give you the vertical load that's going to be causing this beam to crack. Are we good?
Yeah.
Is this
Yes.
example clear? Or this homework?
What was that you said? I didn't understand.
Just want to be sure that this homework is clear to you guys.
Mm-hmm. Mm-hmm.
It has been discussed. I don't want to see an email 5 minutes before the submittal asking for how can I solve this or what's happening here. I thought that you're going to give us the load, very similar to what happened here, right? This P was given to you. Now, in this case, your job is to find out this vertical load is going to be causing this beam to crack. Should I repeat this again? If you're not giving me enough attention, please come here and ask me the question. You don't want to lose this 5 points. Any questions?
Yeah, I have a question about
Yes,
the
please.
selector. So previously we solved the T-beam by dividing the, like on the compression side, Z1, Z2, and Z3, right?
Yes.
So this one is different because of the rebar?
No. When you have, okay, generally speaking, when you have uncracked section, when you're talking about the cracking moment, 3 bars do not count. Ignore him as if you don't see him.
Okay.
This is why even in this, I didn't mention the rebar size or number, right? It looks like 3, yes, but you don't know the size. Rebars here are ignored because we are talking about uncracked section.
Okay.
So actually, the first problem is going to be very similar to the example. The second problem, all what you need to do, I'm going to post this video on YouTube by end of today. So if you like, you can go back and confirm this. The applied moment, which is M, is going to be equal to 10 times P. It's going to be the same as M cracking from here. Therefore, P is going to be equal to M cracking divided by 10 feet. That's it. This is all what you need to do in the second problem. Someone's going to say, how about the self-weight? I said, ignore the self-weight. I'm going to type it here. Self-weight to be ignored. All right? Any questions before we go?
Excuse me, can I ask if you could just put the solutions of the homeworks also online?
Which one?
For all of them, previous one.
Not all of them, because some of them you don't really need to have any solution to it.
But actually, I mean for number 2, please.
Number 2. Number
Yeah.
2, which is this one?
Yes, yes. This.
Okay, I'll post this. No problem.
Thank
Here's
you.
the solution. I'll post it today.
Thank you.
No problem. Any questions before we go?
Professor, besides today's office hour, will you be at all available tomorrow?
What time or what's going on?
Probably like early afternoon, around 12.
Give me a sec. Okay, you have to go now or so? So you don't have to ask your question?
Well, I was gonna start this homework and I'm not sure how long it'll take me, but if I had any questions.
Okay, let's do an office hour. It's gonna be at 1 p.m. How about that?
Okay, yeah, that's good.
Great, we'll do that. All right, so tomorrow, 1 p.m.
All right, thank you.
Thank you. All right, please sign out.
Thank you, Professor.
Thank you.
Thank you, Professor.
Thank you. Thank you very much. Have a good night.
Thank
You
you.
too. Bye.
Professor,
Yes, go ahead.
what's it called? For homework 2, I had a power outage on Sunday and I wasn't able to turn it in, and I emailed it. I was just wondering if there's any way
Did
I
you email it already?
I emailed it on Monday, the day after. It was due. And I was wondering if I could get any points on that. or
I
not.
don't know. I haven't seen it yet. Let me look at it. And which area are you located at for the outage?
Cyprus.
Cyprus.
Yes.